warahmatullahi wabarakatuh. Good morning, dear college presenters, participants. On this morning, we should be thankful to the God, Allah Subhanahu wa Ta'ala, and His Prophet Muhammad Sallallahu Alaihi Wasallam, because for His grace, this morning we can gather and meet by online in the international online seminar with the title From Biomass to Bioenergy. We would like to express our gratitude to the Dean of the Faculty of Agricultural Technology, Universitas Brawijaya, Professor Imam Santoso, for his permission this event can be held this morning. We would like to express our gratitude to Mrs. Dr. Asmaul Mustanirah as the head of the Department of Agroindustrial Technology, Faculty of Agricultural Technology, Universitas Brawijaya, who on this occasion will represent as the Dean to open the seminar. Thank you for Mrs. Sri Suhartini PhD, the Secretary of Department of Agroindustrial Technology, Faculty of Agricultural Technology, Universitas Brawijaya, as a moderator of this seminar today. We would like also express our gratitude to the presenters, Mr. Zhang PhD, Mr. Zhijian PhD, Mr. Hendricks Julius Setyawan PhD, and Mrs. Nimas Mayang Sunyoto PhD, who have been ready to take the time to share knowledge related to our seminar today. Before we start our seminar, we would ask to the participants to obey the rules for this seminar. Please mute the microphone during the seminar. As information for the participants, the confirmation links to claim the certificate will be shared at the end of the session of this seminar. So, we ask the participants can participate from beginning to the end of this event. Before we start the seminar this morning, we invite Dr. Asmaul Mustanirah as represent the Dean of Faculty of Agricultural Technology to open the event today. Mrs. Dr. Asmaul Mustanirah, please welcome.
Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Good morning and best wishes for all of you. Dear the Honorable Guest Speaker, Mr. Yang Xiang, PhD from Tsinghua University, China. Mr. Zhijian from Harbin Institute of Technology, China. Mr. Hendrix and Mrs. Nimas from Department of Agroindustrial Technology, Universitas Brawijaya, and as well all participants of the virtual international seminar on biomass to bioenergy. Thank you for being here with us today. This webinar collaboration Department of Agroindustrial Technology, Faculty of Agricultural Technology, Universitas Brawijaya, with Tsinghua University, Harbin Institute of Technology, Palm Agroindustry Research Group, and Sbistec Research Group. We are very appreciated for it. Before to starting the seminar, that I want to say about the content, bioenergy and biosystem. Nowadays, the existence of research group is strong, crucial to increasing performance in university, specialty to Universitas Brawijaya, linkage of 3 Dharma activity. So, development of scientific competence for academics include lecturer and student. It's very important to implement in the industrial 4.0 with various technology, management, engineering, and tools to improvement. Now, the Indonesia as one of the world's bioenergy suppliers it's a good opportunity to expand our research and development in bioenergy that via future challenge is will to developing bioenergy such as capital, technology, economy, politics, and markets to highlight by value government, community, and economics to synergy in finding the solution about biosystem and bioenergy in the world. Dear everyone, with the virtual international seminar on biomass to bioenergy, we hope that it can be active to support Indonesia academic community to the Asian maker in Indonesia, specialty in academics. That congratulations on joining the virtual international seminar on biomass to bioenergy. Hopefully, what we do today will simultaneously benefit to us and Indonesian development. I hope today will be full of learning and full of good discussion. Thank you. Success for this virtual international seminar. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you for Mrs. Dr. Asmaul Mustanirah for the remarks. For the next, we invite Mrs. Sri Suhartini PhD as the moderator to guide this seminar today. Mrs. Sri Suhartini PhD, please welcome.
Okay, thank you, Mr. Kamal. So good morning, everyone. Before we start, please, I would like to introduce myself. My name is Sri Suhartini. I will be the chairman for today's virtual international seminar on biomass to bioenergy. And as been mentioned by our head of department, that actually bioenergy is one of the key to strengthening the energy security, not only in the world, but also in Indonesia. And we know that actually Indonesia government is also very keen to expand research and development, not only in biogas, but also in other routes for bioenergy source. We know that Indonesia has a vast and abundant resource for biomass, such as palm oil waste, rice straw, sugarcane, and etc. And we need more expertise in order to help the government to further advance the available resource. For today's event, the aim is actually to provide a platform for the academic and also for researchers to have an active discussion in order to enhance our knowledge for valorizing biomass, not only in biological routes, but also in chemical and thermochemical routes. Okay, without further ado, I would like to read the schedule for today's event. So the first session will be by Dr. Zhang. The title is about hydrogen-rich gases fuel, low-cost transport and application. And this will be followed by the second keynote speaker, Dr. Zhijian Wan. The title is about from biomass to gasoline production, followed by Mr. Hendrix, Dr. Hendricks Julius Setyawan will talk about Glycerol combustion, study of biodiesel waste to energy. And the last speaker is Dr. Nimas Mayang with the title Enhancing Biogas Production in Two-Phase Anaerobic Digestion, the Role of Biochar. After all the keynote speaker present their PPT, there will be a question and answer around 50 minutes and followed by a closing speech. And hopefully for today, virtual international seminar will be finished by 12. And as been mentioned by the host, that the certificate and also the registration for the participant will be shared at the end of the virtual event. So without further ado, I would like to introduce our first keynote speaker. Dr. Yang Zhang. He finished his doctoral degree in thermal engineering in Tsinghua University, China, and he has experience as a research associate in University of Western Australia, and now he works as an assistant professor at Tsinghua University, China. And about his research expertise is in combustion physics and chemistry, syngas combustion, slurry fuel combustion, and biomass pyrolysis and combustion. Okay, please, Dr. Yang Yang, time is yours for 25 minutes presentation.
Thank you, Chair, for your kind introduction. I will try to share my slides, just seconds. Okay, morning. Is my slides clear? Clear to you? Okay, I guess the slides is already on your screen. So
yes,
yeah, so good morning. Thank you. So good morning, ladies and gentlemen. My name is Yang Zhang from Department of Energy and Power Engineering of Tsinghua University. I'm very happy to be a part of this wonderful webinar. Thank you very much for inviting me. Today I'm going to share some of my thoughts on the hydrogen-rich gaseous fuels. But at the very beginning, I would like to say a few more words about where I'm from. So Tsinghua University is established in 1911. Next year we will have our 100th anniversary ceremony. I guess in the past 10 years, Tsinghua has been developing very fast and quickly climbed to the level among the top universities ranked list. For example, let me give a little pen. For example, the newest QS World University ranking give us number 15, and the newest Times Higher Education give us the 23rd of the whole university list. And I would like to also mention that we have probably the most beautiful campus. The Forbes journal evaluate the beauty of the campus on 2017, and we are ranked in the top 10 most beautiful university campus. This is the picture of our overview. My lab is just over here. There's a building of all the mechanical engineering now belong to us, the energy and the power engineering, because we are a very important section for mechanical engineering. The Royal Garden, so you can see all kinds of traditional Chinese style architectures. It's very beautiful. I guess the old gate, the chancellor's office, the HR office, and all the pavilions, the Chinese traditional bridges. We also have very modern architectures such as our library, the student dormitory, the art museum. I mentioned this because I want to post some advertisement. I think one of the weakest point of Tsinghua University now is the level of internationalization. Only less than 1/10 of the students are international students compared to the other top universities such as MIT, Harvard, Stanford, Oxford, Cambridge. The number is too low. So if you are interested, you can apply for exchange program in Tsinghua University, and or a PhD or master degree. I think it will give you a very good opportunity to study and have fun here. Of course, we need all degree of different diversity and also different cultures to make us more smart. a little more introduction of my institute. About we call it the Institute of Thermal Engineering. In this institute, we have roughly 30 faculty members, including 14 full-time professors. We have very strong and modern lab facilities. Our research interests covers the combustion and pollution control, the R&D of the better combustion technology, and also biomass and coal pyrolysis gasification. Basically, I guess we have developed a very good technology for direct biomass-fired boilers. For combined CHP production, our technology exported to Thailand and some Middle Asian countries. The largest unit is now the 100 megawatts. I think they are working very good using this kind of technology called food as the better combustion. Uh, uh, in addition to this, we also do some fundamental research like multi-phase flow measurements and solid phase utilization. Okay, so that's all my brief introduction of my institution. Let's go back to the topic. Today, I'm going to cover the following contents. The first, the motivation of low-cost hydrogen transport and application. And then I will give the definition of hydrogen-enriched natural gas. And then follow this part, I will give you some fundamentals of HENG combustion characteristics in real combustion devices. So the story starts with the fact that the situation that utilization of renewable energy is booming. I guess China is the world's largest developing country. The issues that we are facing can be a reference for the other fast developing countries. I will share some of the data statistics to you and share with you what we thought and our ideas how to overcome all these difficulties. Uh, that's the power unit installed capacity in China 5 years ago. You can see the renewables like wind and solar take only tiny slice of the total total energy mix. How about biomass? I think biomass is even lower than this line, so it does not show on this part. But now you can see that the wind and the solar take a very large share. Only 5 years. For example, the solar increased from 15.9 gigawatts to more than 200, and the wind is almost triple of the installed capacity. So the faster developing of the renewables cause some problems. What's the problems is the first one is that the renewable energy is all intermittent. Similar things to biomass, I guess. I always heard the news that during the summertime, I mean the July to September, I guess, there will be bushfire in Indonesia. Probably because at that time there is abundant biomass straws, but this kind of supply is also seasoning. We cannot control the time as our demand. Similar things to solar and wind. I think you may have already heard of this. You are familiar with this, but one thing is not always considered is the uneven distribution of the renewable energy. I think this is also true for Indonesia, because I think Indonesia is a very a roughly narrow but long country, and also composed of thousands of islands. For China, if we draw a line here, you can see all the renewables concentrate to the northwest part. Renewable resources concentrated on the northwest part of China. However, this part of China only contains of 6%, roughly 6% of the population, and only 8% of the power demand. But on this part, we have the major population, the major power demand. The question is, we need to transport the energy and the power from this part to this part. We can build, very strong electricity grids, but the distance from these two is roughly more than 3,000 kilometers. Very expensive. So we need to figure out, a more economical way to transport this power and storage this power, and we need to use this power on our demand. So that's why we are talking about hydrogen. Hydrogen is an easily produced energy carrier from all kinds of renewable recovered energies, such as also biomass included. Next slides, I will show you how to produce hydrogen from biomass. The more important thing is that hydrogen can be storable, transportable, and we can use it on our demand. So basically, when we have our renewable energy at hand, we can produce hydrogen using electrolysis from solar and wind, or we can use gasification or pyrolysis, producing hydrogen from biomass. Once we have hydrogen, we can storage hydrogen and transport hydrogen to users. If we need heat, just burn hydrogen to generate heat. If we use electricity, we can use fuel cell, or we can burn hydrogen in turbine or gas engine to generate electricity. That's our concept. That's how we can produce hydrogen using biomass. I think this was done in the University of Western Australia when I was doing my PhD, postdoctoral project there. We developed a technology, we call it integrated pyrolysis and tar cracking technology. When we have all kinds of pyrolysis, a biomass, we feed the biomass into a pyrolysis unit. For example, here, that's the demonstration unit we built in Australia. We will have raw syngas and tar, and use the biochar as a catalyst to crack the tar and raw syngas. We can get hydrogen-rich syngas. If we want to use the gas distributedly, we can just use gas engines for CHP generation. If we want to transport this energy to the other places for long distances, we can use water gas shift to purify the hydrogen, or we can use PSA technology, a pressure swing absorption technology, to get a relatively pure hydrogen and transport the hydrogen to the other places and use the hydrogen. Okay, so that's the key ideas of this concept. The next question is, can we storage and transport hydrogen in a low cost? Generally, that's a diagram for hydrogen transport and the storage technologies. I think this diagram implies the energy cost of compressed hydrogen storage and the liquefied hydrogen storage. For example, if the most commercialized the technology for hydrogen storage and the transportation is the hydrogen technology. These two lines shows the compressed technology. Actually, if we increase the pressure, you can see that the gravimetric hydrogen density actually decrease. Why? That's because if we have higher pressure, we need thicker walls to contain all this hydrogen. So basically, although the volumetric hydrogen density is increasing, but the cost will be very, very high. If we store the hydrogen in 350 bar, 9% of the stored energy will be used to compress the hydrogen. If we use 700 bar, that is the standard of probably Japan and the US, 13% of the energy will be consumed. If we want to liquefy the hydrogen, because the liquefied hydrogen can get a very high gravimetric hydrogen density. Renewable energy to produce hydrogen, and we mix the hydrogen with natural gas and transport this kind of hydrogen using natural gas pipelines. Pipeline is already there. It's already there. We can directly use them. It will release the renewable energy curtailment and also reduce the carbon level of domestic gas supply. There will be a lot of advantages for hydrogen combustion. The first one is hydrogen has broader flammability range. It will because the broader flammability range, it will give you a more a stronger flame, so the flame can sustain a lower and leaner combustion. It also has some potential of more stable combustion. What is more important is we can have lower soot and CO2 emissions. That's a main impact to our cleaner future. Okay, that's our concept. But hydrogen as a fuel is very special. It's a very unique fuel. You can see that the hydrogen, these plots give the energy density of hydrogen. You can see hydrogen is here. It has very high gravimetric energy density. It's here compared to the other, hydrocarbon fuels. Hydrogen is here, but because hydrogen is gaseous fuels and the density is very low, so there will be very low volumetric energy density. So this problem, the thermal far away from natural gas. If we compare its features to natural, almost 3 times to natural gas, and the density is can be even ignored. Here the CP value, the specific heat, is much higher than methane. This will make the combustion characteristics of hydrogen, quite different from natural gas. So questions will naturally raised: is hydrogen blending? Blending will have considerable impact on the natural gas and the user. If there is a significant impact on the end user, this technology is doomed. We cannot use it, right? So there must be a limit, more friction for hydrogen blending. This, if you check the literature, different literature will give you different limit value. That will be a reason for this different value, right? So I will explain this the reason in the following slides. The second question is, how about the emission? Because the adiabatic flame temperature of hydrogen is slightly higher than natural gas, and NOx is exponentially increase with temperature. So probably nitrogen will give you higher NOx emissions. That will to the opposite of our original idea that hydrogen is more clean, right? So these two issues must be solved before we can use it. I think this topic has been studied in the European for more than 15 years, but China is just a start. We are very fast. Okay, so first, let's talk about the limit of hydrogen combustion in a homogeneous reacting flow. Just now I mentioned that the energy content by hydrogen is quite different, right? And also the diffusivity is quite different. So now in this system, we put the diffusivity aside, only consider about the energy. We use a PSR model to simulate this kind of process. We have several fuel and oxidizer put into a system. This same system is homogeneous, burned, producing the products outside. There will be heat loss to the environment. This heat loss can be used for generating power or heat, right? If you give the equations to this system, the energy equation, species equation, chemical equation, I will skip the detailed math and directly go to the results. Okay, we will have several solutions like this. Sometimes they will give us a S-shaped curve with distinguished ignition and extinction point. And sometimes if we change the initial temperature or the residence time, we'll have this kind of monotonic combustion phenomena. We plot all the situations in a diagram, we can get this kind of phase diagram. Different combustion mode, such as mild combustion, no combustion, feedback combustion, and high temperature combustion can be all added to this plot. This point is very important. I call it critical temperature because at this point, all the lines cross over together. So this point can be representative for the overall, combustion regimes. If this temperature changes, it means the extinction, the ignition will be, strongly affected. Okay, so for hydrogen enriched natural gas, if there is no hydrogen here, the value will be here. If it is 100% hydrogen, the value will be here. And if we can see that as the increase of hydrogen mole fraction, the curve go flat like this at the very beginning and then quickly decrease. That means, okay, if we have very high hydrogen concentration, there will be a significant impact on the safety of the natural gas end user. However, if we can maintain the hydrogen concentration, hydrogen mole fraction within this range, it seems okay, right? This value is roughly 30%. Okay, so for most of the literature, they will give you a result that the limit of hydrogen mole fraction is roughly 30% in natural gas. Okay, this is consistent with the literature. However, just as I mentioned, I didn't consider the transport phenomena, the molecular transport phenomena. Uh, but hydrogen has a very strong molecular transport. It will play an important role in the overall combustion process. Okay, so next, we studied hydrogen enriched natural gas combustion in a real flame. That's the experimental facilities I used to do the test. I have a count flow nozzle. We can generate several, a very flat flames here. And I use some laser to shoot this flame, get the information of the flow field and the chemistry information. And we can give back to some of the ideas of how hydrogen affects the overall combustion process. Okay. Yeah, that's the data we get. We first measure the extinction limit. Extinction, it means if we keep on increase the velocity or keep on increase the stretch rate, there will be shorter time for the reaction to happen. If there is not enough time for the reaction will, the heat release of the reaction will be minimized. In that case, there will be a sudden extinction. Extinction is always a very, a very serious. Yes, so that's pure hydrogen. That's pure methane. And this is another hydrogen carrier. We call it methanol. And that's the hydrogen blended methane. We can see, okay, so the value is here. These lines are my modeling, but I do not want to see the modeling too much. Just look at the experimental results. You can see the extinction limit is roughly 500, right, for pure methane. However, if we keep on increase the hydrogen blending ratio, it can be go as high as 1,000. Yes, that means the hydrogen can be sustained at a high strain rate. That means hydrogen flame is more stable, right? It will has lots of impact on the combustion. But just now, for my homogeneous analysis, I tell you that up to 30% or 40%, there is no significant difference. Okay, so that means the difference is caused by the diffusion process. Okay, so next, we fully analysis the preferential diffusion effect of hydrogen. What is preferential diffusion? Just look at this flame structure plot here. We combine the mixture of hydrogen, methane, and oxygen as a feedstock. Here is the flame, so there will be a temperature increase. You can see that the drop curve here, this layer for hydrogen is much thicker than methane or oxygen. because the molecular weight of hydrogen is very light, right? It will go much further for this system. Because this kind of preferential diffusion, it makes the flip front either hydrogen rich or hydrogen lean, right? It's different from the homogeneous systems. Okay, so it gives you that the extinction strain rate will roughly monotonically increase with the hydrogen compression ratio. And if the hydrogen compression ratio is higher than 40%, it will give you a very sharp increase. Okay, and we try to mimic this system using different normalized non-dimensional extinction limit plots. Okay, you can see this dot is a pure diffusion flame. That means the diffusion will give you a very important rule in this system. This one is PSR, homogeneous, no diffusion at all. This is the premix system. Premix system just within these two range. When you can see when the hydrogen ratio is low, the premix system is quite close to the PSR. It means for premix system in this range, the diffusion is not so important. However, if we further increase the hydrogen content ratio, the diffusion will become very important. For diffusion systems, the diffusion plays, always plays very important role in these systems. Okay, let's give you a rough explanation that why different researchers, different papers give you different limit hydrogen blending limit. That's because the system is different. Some burners using the diffusion combustion burner, some burners use premixed, and for example, for gas turbine or the GDI or HCCI engines, it is more close to this line. Okay, so sometimes this problem is case sensitive. We need to study all these common facilities one by one, and then we can give you a limit range, a limit value for hydrogen blending. Okay, that's the complexity of this problem, but we are still on the way. And I think lots of people in the world, for example, from the European, from the US, are still working on this project. What's the limit for hydrogen blending? And this limit shouldn't have any considerable impact on the end user. At this moment, the well agreed value is 10%. So people think of 10% hydrogen in the pipeline will have no significant impact on the end user. People are trying to increase this value to 20% or 30%, but we are still evaluating the risk of this technology. Okay. More importantly, the pressure effect also complicates the combustion limit of phenomena. For example, hydrogen, that's ethylene, that's propylene. These two compounds are mimic the impurities in hydrogen produced from the from biomass pyrolysis. We can see, okay, at a different pressure, and it gives you different curves. That means pressure effect is very complex. So we also need to think carefully about the pressure effect on this topic, on this technology. The next part is about the NOx emission. Hydrogen have slightly higher temperature than natural gas at the same equivalence ratio. So we did some tests and find that yes, the hydrogen give you a little bit higher NOx emission, but this NOx emission can be suppressed by some technologies such as FGR. If we give you FGR ratio to properly to 20% FGR flue gas recirculation technology, you can significantly decrease the NOx emission. Okay, so that one big problem. We just add some FGR. Just add FGR to the system. That's okay. Okay, so that's the fundamentals for HENG combustion. Next, I will give you some of the results of application HENG in real important concept must be given at first index. The Webby index is this index to characterize this phenomena. We can know that if the Webb index is close to each other, that means the gas can be replaced by each other. Okay, if we add some hydrogen into the system, you can see the Webb index first decrease from 51 something to 44. Actually, that's a very strong decrease. And then further increase. But we are talking the range here, right? Not here. So basically, add hydrogen in the system, it will give you less energy. The second issue is the stoichiometry of hydrogen and methane combustion. Look at the equation here. For methane, 1 mole of methane will need, you can see that's 9.52 more of air, right? But for hydrogen, it needs much less air for in the system. In our real combustion devices, the air is introduced either by forced fan, fan induced air blowing, or by injection, air by entrainment. Either of these two technology won't change the air supply. So basically, that means if we use hydrogen blending in the natural gas, the combustion excess air ratio will also change. This is the plot, okay? This is the original excess air ratio for natural gas. If we it makes them more leaner. Leaner means not lean, means lower temperature, less stability. That's the thing we also need to consider. Okay, so put these two things in our mind, we can do some, real combustion device test, engine test, because the gas engine is more suitable for distributed energy supply. Everyone can drive a car, can do this. For gas turbine, it's more complicated. For boilers, it needs large scale to increase its efficiency. Okay, that's the system I built in my lab. I did some of the experiments and find the first, this slide shows the indicated power and indicated thermal efficiency. Okay, we can see if we add some hydrogen in the system, the indicated power actually, you can see increase. For the relatively low excess air ratio, the effect is not so significant. But for very lean cases, you can see the increase is much stronger, right? That means you can also see the data from this figure. That's the thermal efficiency. Okay, so this range, no big difference. But for this range, very lean ranges, okay, the hydrogen will largely extended the stable operation limit, right? Okay, that means hydrogen is is a very good additive for gas engines. It can extend the lean operation limit. Leaner means lower temperature. Lower temperature gives you less NOx emission. However, hydrogen is very tricky things. Hydrogen, the adiabatic flame temperature of hydrogen is higher than nitrogen, right? So we go to the emissions. These three plots give you the break-specific unburned hydrocarbon emission, CO emission, and NOx emission. You can see, okay, if we blend in some hydrogen in the system, the unburned hydrocarbon, the CO, will decrease. Okay, that's the highest hydrogen concentration curve. Hydrogen increase, the emission of unburned hydrocarbon, the CO decrease. But for the NOx, especially at a strong burning range, if we add more hydrogen, the NOx emission dramatically increase. Okay, so that means this range is not a proper way to operate the engine, right? We can operate the engine here, which can both maintain the very good combustion, general combustion, performance, and also here maintains the emission in a very reasonable range, just here, this range, from 0.3 to 0.4, right? Okay, so basically we have options, we have methods to deal with it, but why this kind of phenomena is caused by hydrogen? We also did some of the numerical simulation to see what happens inside the engine. If we increase the hydrogen velocity, hydrogen mole friction, we can see the temperature will decrease at the very beginning, but will increase at the very beginning, but decrease when the crack angle goes to the end of this cycle. And similar things to the similar things at a higher excess air ratio. In that case, it makes the cylinder pressure goes higher. Cylinder pressure goes higher means you can have higher power and a higher thermal efficiency. Well, it also gives you higher peak temperature. I collect all the NOx emission data and plot the NOx emission with burn zone temperature. You can see, okay, it first merge to each other for different cases, and the second it follows exponential way. That means the NOx emission is controlled by the thermal NOx mechanism. Thermal NOx mechanism. A thermal NOx mechanism is is sensitive to temperature increase. That means we can control the temperature by suppress the NOx emission. Okay, so that gives us several main ideas, but we still facing a lot of challenges. We need to because at the first hand, at the first place, we do not know the hydrogen concentration in the pipeline at this moment. So there will be some very smart control system to control the air and to control the excess air ratio to maintain the engine working at its suitable operation range. That's the first thing. The second thing is the modification shouldn't be very very large. Should be limited to a very low cost level. Otherwise, it will give you too much liability on the economy. That won't be acceptable by us developing countries. Okay, that's all the ideas I want to share. In a short summary, hydrogen as a universal secondary energy carrier can be used to solve the renewable energy transportation and storage problems. And hydrogen enriched natural gas, that means we blend hydrogen in the pipeline, can be an important first place for the large scale utilization of hydrogen energy. And the exploration of limit of hydrogen ratio in the pipeline is still ongoing. We are still producing new data to support our ideas of the limit, upper limit of hydrogen blending ratio, and the combustion limits and the NOx emission is the two key issues which need to be solved for HENG domestic natural gas pipeline balance. Okay, so that's all my presentation. A little bit exceeded the time. Sorry for that, and I welcome your question and discussion in the later section. Okay, thank you.
Yeah, thank you, Dr. Zhang. Very interesting presentation about combustion for hydrogen production, and we know that actually hydrogen will be one of the alternative clean energy in the future. So maybe because we are running late, so I would like to request the second presentation to be ready. But before that, I would like to read a short CV of Dr. Zhijian Wan. So Dr. Zhijian Wan finished doctoral degree in chemical engineering from University of Western Australia, and he has so many work experience as a research assistant at the University of Western Australia, at WUXI, at PAX, and also research assistant at Hutchison Medipharma. And now he works as a research fellow at School of Science, Harbin Institute of Technology, China. And his main research expertise in catalyst synthesis and characterization, methanol conversion and hydrocarbon, hydrogen production, waste conversion, and renewable fuel synthesis. Okay, without further ado, I would like to ask Dr. Zhijian to present. Thank you.
I'll just share my screen. Just give me 1 second. Sorry, I just.
Yeah.
So
while we, don't worry, takes your time. So while we are waiting for Dr. Zhijian, I would like to inform for the audience, you can ask the question by typing into the Zoom chat, or if you are joining us from the YouTube, you can also ask question from the YouTube. I will read all the questions hopefully by end of the session.
Okay, now I'm ready.
Yep.
Sorry for the delay. And first of all, thank you for the introduction. And because I think we're running a little bit late, I'll just go straight. Today, my topic is biomass to gasoline production. So possibly you already got the idea from these two pictures here. So we basically can convert solid plants. In other words, biomass into biofuel. In this case, in my case, it's gasoline. So you can use gasoline to drive a car from biomass conversion. So the concept. Basically, biomass is the waste we don't need, almost anything we don't need. We call it biomass. And from biomass to gasoline, it involves mainly 3 steps. First one is biomass to syngas synthesis, and the second is syngas to methanol. Last is methanol to gasoline. The whole process looks quite fancy because we can convert solid into liquid fuels. But in reality, it involves extensive hard work and also very complex work, as will be discussed in my following slides. The first step, we need to convert biomass through pyrolysis. I take the wood chip as an example for biomass. So first of all, what we need to do is we need to break the chemical chains in the biomass. What we should do is we put the biomass into a reactor. The reactor up to very high temperatures, up to 800 degrees Celsius. In the absence of oxygen, here we do this pyrolysis without oxygen, because if we have oxygen gas in the reactor, we are going to burn the biomass rather than to make it to be converted. So in this case, in the reactor without oxygen, biomass can be converted into its compositional elements. That means we have a lot of gases containing oxygen, carbon, hydrogen, and others gases containing nitrogen and sulfur. So at the end of the reactor, what we have is a mixture of gases, mainly including CO, hydrogen, and CO2 and methane, but also containing a small amount of ammonia and hydrogen sulfide of course, we also have the solid carbon that cannot be converted. What we should do next is a step called gas cleaning. Because for the next step, because for methanol synthesis, the reactant is only CO and hydrogen. We call the gas mixture syngas. So we need to either remove the impurities in the pyrolytic gas, or convert the gases into a gas mixture containing mainly CO and hydrogen. So what we should do here is, first, we need to remove the solid carbon. So we introduce the pyrolytic gas into a separator called the Cyclone Separator. Here, the solid carbon can be separated. So the solid carbon come out from the separator at the bottom, and the gas going up. And the next stage, the gas mixture without the solid going into absorber. Here ammonia and hydrogen sulfur can be absorbed. So at the end, we have a smaller amount of gases, mainly containing CO, hydrogen, CO2, and methane. Next step is we call gas conditioning. As I mentioned, for methanol synthesis, the reactant is syngas containing CO and H2. But in the gas mixture here, we still have CO2 and CH4 methane. CO2 is not a problem because people have reported CO2 is actually involved partially in the methanol synthesis. So we mainly need to convert methane into hydrogen or CO. There are two reactions involved. First one is called water-gas shift reactions. So CO can react with water in the presence of a catalyst, mainly copper and zinc based, at temperatures in the range of 200 to 450 degrees Celsius. We can have a gas so water can be converted into hydrogen, but we have a CO2 as a byproduct. But as I mentioned, CO2 is not a big problem. A second reaction is called methane steam reforming. Also, methane can react with water steam in the presence of a nickel-based catalyst and at very high temperatures in the range of 500 degrees C to 900 degrees C. So we have a gas mixture of CO and hydrogen. This process, we call it gas conditioning, because we not only need to convert the impurities into CO and hydrogen, we also need to adjust the hydrogen and CO ratio into about 2 to make it right for methanol synthesis. Once we have the gas cleaned and conditioned, we can go to the next step, methanol synthesis. Methanol synthesis is a very mature technology. So basically, syngas with mainly CO and hydrogen with hydrogen to CO ratio about 2 in the presence of copper and zinc catalyst at around 250 degrees Celsius, but under very high pressures in around 5 to 10 megapascals. Here, the syngas can be converted to methanol. So it's because it's quite mature, it's not much to talk about, but it's quite amazing because at this stage, we can convert biomass, the solid, into a liquid methanol. Just give you a brief summary for this process. So basically, this is a flow chart for biomass to methanol synthesis. So biomass feed into a porous reactor, convert in the reactor, and the residues is separated. Carbon can be separated by a cyclone separator. The gas mixture goes through cleaning, conditioning, and we can feed the gas into methanol synthesis process. Because during methanol synthesis, water is produced, and also another byproduct that methyl ester is also produced. If you want to get very pure methanol, we do additional step called methanol distillation. At the end, we have methanol. We can call this renewable methanol because methanol in this case is produced from renewable resources, biomass. Okay, now I go to next stage to convert methanol into gasoline fuels. So it's quite straightforward. Methanol is a feed, is a reactant, and for methanol synthesis, for gasoline synthesis, we use a catalyst called ZS5, zeolite. At temperature around from 350 to 370 degrees Celsius, and the pressure 1 to 2 megapascals. In the reactor, methanol can be converted, and we can have a product mainly in the gasoline range. So this table shows the products from methanol conversion. You can see these products here, listed here, are the main product, but in reality, from methanol conversion, it actually have more than 100 chemical species. So this reaction is quite amazing. As you may remember in the textbook of chemistry in our senior high school, what we know for the chemical reaction is A and B as a reactant, and we can have a C and D as a product. But here, as you can see, we only have methanol as a reactant, and we have a bunch of different chemical species as a product. So that means the catalyst must have do a very important job in converting methanol into gasoline products. So in this slide, I will talk about what is a catalyst. The catalyst have a formal name ZS15. So if you want to know what is Z for, what's S for, what M for, you can Google it. I'm not talking into details here. So basically, it's an aluminosilicate material based on silica, but with a small portion of the alumina as well. So this material has 3D microporous channels. The channels have a pore size about 0.5. The pore size is very small. We cannot see it by our naked eyes. So this material also has very high acidity. This is why methanol can be converted, and also because it has the channel with pore size of in the macro shape selectivity. What does the shape selectivity mean? It means only those are small steps. Further, the primary product be converted into gasoline range hydrocarbons containing mainly aromatics. So the figure at the bottom show you how complex the reaction is. It's a cycle of dealkylation and dehydrogenation press. I hope you get a brief. And this photo is the actual empty methanol conversion to gasoline plant. This one is in operation in 1985 in New Zealand. Has stopped very quickly because during that time, because oil crisis, we don't have enough crude oil to invent this process to convert methanol into gasoline. Methanol can be converted from can be synthesized from crude oil. But after that, we get out from the oil crisis shortly, and now it's not for methanol conversion to gasoline. It's mainly for methanol synthesis. But this one is a big one. It's have a production capacity of 14,000 barrels of gasoline per day. It actually can produce 1/3 of the daily demand gasoline for New Zealand use. This flow chart is basically for the photos I showed you in the last slides. But I'm not going to talk to you into detail. But for the flow chart, I just want to get your attention on the red highlight here. So in the real operation, normally it has 4 reactors in operation and 1 is in regeneration. Why we have one reactor in regeneration, not put this one also in operation? Because the catalyst for methanol conversion can lose its activity very quickly. As I mentioned, the catalyst has 3D micropore channels and it has very small pores. And during the methanol conversion, during the reactions, there are some molecules are not doing very good job. They don't want to come out from the channel to be product. They just continue to just stay in the channels and continue to react with methanol and grow bigger. Eventually, they grow big enough to block the channels. So we call this big molecules, chemical molecules, they grow bigger to growing big. They grow too big to block the channels, converted. At this end, the catalyst will lose its activity. Because the coke is carbon-based, so we can regenerate the catalyst back to its activity. So what we do is we take out the reactor and introduce air in, so we can burn the coke. We can burn off the coke, and the channels is opened again. Then we can put the catalyst back to operation again. So this, there are 2 approaches to improve the activities, not just by regeneration. There are also other 2 approaches to improve the activity of the catalyst. One is to shorten the diffusion process by synthesizing nanocrystal catalyst. Another one is because the coke form is mainly because the channels of the catalyst is too small. So what we can do is to create large pores, massive pores in the crystals. In this case, even the molecule grows a little bigger, it can still come out as product, even the product is not what we want, but it's better for them to stay in the channel to form coke and block the channels. This image here, they are all densified catalysts, but you can see they have a very different morphologies, from nanometer crystals to micrometer crystals. Take two as an example to see the difference of their performance. So here I take one with crystal size about 100 nanometers, so 0.1 micrometer. Another one has crystal of 13 micrometers. So the macron crystal catalyst has roughly 130 times larger crystal than the nano crystal catalyst. And from the nitrogen phase sorption exosome on the right side, we can see the nano-crystal catalysts not only have small crystals, short diffusion paths, it also has massive pores. That means large pores. But for the macron crystal catalyst, it basically just only have very small pores without large pores. And for the performance in terms of mass conversion as a function of time, we can see here the macron crystal catalyst drop, the activity of the macron crystal catalyst drops quickly, but for the non-crystal catalyst, it can maintain for longer time. The nanocrystal catalysts actually have about 7 times longer lifetime than the macron crystal catalyst. To look deeper, we need to know why the two catalysts, they are all densified catalysts, they can have a very different performance for methanol conversion. So this image here is the nanocrystal catalyst and the macron crystal catalyst after use. As if you remember, for the image I show you in the previous slides, the nanocrystal catalyst and also the macron crystal catalyst, they are quite clean and clear. But for this one, we can see there's many small fractions presented in the along with the crystals. So these are the coke, are the carbons, and for the nitrogen isotomes at the right side, we can say both catalysts for the nanocrystal and the macron crystal catalysts, both catalysts, the macro pores drop a little, but the macron crystal catalyst drop more than the nanocrystal catalyst. And the nanocrystal catalyst also retain its macro pores, as you can see in the isotomes. And it's still not enough. We still need to look deeply why the nanocrystal has longer lifetime than macron crystal catalyst. Here we look deeply for the nanocrystal catalyst. You can see from the TM, the transmission electron microscopy image, we can see that there is a layer of a coke formed around the catalyst, around the crystals. And that's why it looks not that clean, not that clear, because there's amorphous carbon presented in the along with the catalyst. And from the EDS mapping, we can see on the outside of the crystals, the carbon intensity is higher. That means the nanocrystal catalyst formed more external coke, but for the macron crystal catalyst, it's mainly formed internal coke. As you can imagine, internal coke is those formed in the channels. Then, as you can imagine, internal coke is more harmful than the catalyst activity. But you may wonder why the external coke is not that harmful. So we need to look into the properties of the coke. So we dissolved, by doing this, we need to dissolve the crystals and isolate the coke out. Here, this image is used for the coke. You can see the like strings because they form as a layer on the outside and external surface of the crystals. And from the nitrogen isotops on the right side, we can see the carbon actually have a large pores, has a massive pore. What does that mean? This means even there's carbon formed, this coke are formed on the outside and external surface of the catalyst. Because it has large pores, the methanol still can go through these pores and enter the channel of the catalyst. That means the coke doesn't stop the methanol going to the catalyst to be further converted. At this point, we know why the nanocrystal catalyst has longer lifetime than the macrocrystal catalyst. To give you a brief summary for the coking, for the deactivation of the catalyst, here, for the nanocrystal catalyst, it forms mainly porous external coke. The coke mainly formed at the outside, at the external surface of the crystals. And this coke has massive pores, has large pores. This enables nanocrystal catalyst to have longer lifetime. But for the micron crystal catalyst to have large crystals, internal coke are mainly formed. The internal coke is more harmful than for the catalyst activity. So the micron crystal catalysts have a short lifetime. At the end, I want to give you a brief introduction about the synthesis of the catalyst, the SM5. So basically, it involves 8 steps. So firstly, we mix the reactants, the alumina source and silica source, and also a template, and we stir these mixtures for 20 hours, 24 hours, roughly 24 hours, depending on your sensitive reactions. Then we transfer structure, and also, of course, the hard work from the organization committee and the opportunity for me to present my work here. Thank you.
Yeah, thank you, Zhijian. We will provide a time for question and answer at the end of the session. Sure. So before we move to the next presenter, I would like to present you a very short video of please have a look, and then you can have just like a little break or before we move to the next presenter.
The city of Malang has become an icon of education in Indonesia. At the regional level, there are at least 62 public and private regional institutions in Malang. One that interests students is Universitas Brawijaya. Agricultural technology is a branch of science focused on the processing of agricultural resources using modern technology for the improvement of human welfare. The Faculty of Agricultural Technology, Universitas Brawijaya, was officially established in 1998.
Become a leading faculty in the fields of agriculture that is recognized at the international level and actively contributed to the national development through research, teaching, and community services is our vision. We push the research boundaries in the agricultural technology through innovation and collaboration with our local and international partners. The cutting-edge facilities within our faculty to provide a platform for every student to thrive.
The Faculty of Agricultural Technology consists of 3 departments: Agricultural Product Technology, Agricultural Engineering, and Agroindustrial Technology. Teaching and learning activities at the Faculty of Agricultural Technology, Universitas Brawijaya, are optimized using various innovative learning methods. Discussion and presentation help to improve students' critical thinking, teamwork, and communication skills. To support the research activities, we provide a total of 21 laboratories equipped with modern and cutting-edge technologies to stimulate agricultural-based industries. The pilot plan and entrepreneurship laboratory improve learning experience and prepare our students to face the real-world market and industry. Besides academic facilities, we also support the non-academic aspects of student life. There are 9 student clubs to accommodate the interests and talents of our students, as well as to improve their soft skills. The Faculty of Agricultural Technology always strives to achieve the best. Our lecturers, laboratory assistants, and students achieve new things every year. Collaboration with domestic and overseas institutions drive the faculty to explain the latest innovations and trends in the area of agricultural technology. We will always provide the best quality of education and commit to producing high-quality graduates. In the spirit of the motto of the Faculty of Agricultural Technology, Universitas Brawijaya, do the best towards perfection. We are ready to strengthen the agricultural technology of Indonesia.
Yeah, that's briefly a short video telling us about the profile of our faculty. And for your information, our department is Agroindustrial Technology. We have a undergrad, master, and also doctoral program. So if you have any staff or any future students to join our institution, please welcome. Okay. So we are moving to the third keynote speaker, Mr. Hendrix. So I would like to briefly introduce him. So Dr. Hendricks Julius Setyawan, he graduated from Universitas Brawijaya for his bachelor, and he finished his doctoral degree in University of Western Australia, I think in chemical engineering, and works experience at the moment. He works at Department of Agroindustrial Technology, Faculty of Agricultural Technology, Universitas Brawijaya, but he also has experiences as a research associate at University of Western Australia. His research expertise is about bioenergy, pyrolysis, combustion, renewable energy, and also energy engineering. It goes similar to his research experience. He has many research on combustion, waste to bioenergy, like biodiesel, and also waste to resource. Okay, Mr. Hendricks, your time is yours. 25 minutes for the presentation. Thank you. We couldn't hear your voice, Pak Hendricks. Yeah.
Is it better now?
Yeah.
Okay. Thank you, Chair, for the kind introduction. So actually, I was a research assistant in the CFA lab along with Zhijian. So yeah, we did a project together on spent tire pyrolysis. So we separate lots of chemicals and stuff. So it was a very fun time back a few years ago. Okay, so for first, I'd like to say thank you to Yang and Zhijian for the time and their willingness to come here to our department to present their work, the previous work. And okay, so for my talk today, I'd like to address glycerol combustion. So this is one of my research. Glycerol combustion, study of converting biodiesel waste to energy. So the question is, what is biodiesel? What is energy? So if you're not familiar with biodiesel production, so pretty much it looks like on this slide. So to convert biodiesel from triglyceride, you're gonna end up cutting the fatty acid. Hang on, let me check this. There's a color. Yep. Yeah, basically cutting the fatty acid out of the backbone of the triglyceride, and then you're gonna add methanol with the help of sodium hydroxide as a catalyst. Then you'll have fatty esters. It depends on what alcohol you're using. It can be fatty methyl esters if you have methanol, or ethyl ester if you have ethanol, for example. And so this is what we commonly biodiesel. And then the byproduct of this process is actually glycerol, or glycerin in common term. So this was the backbone of the triglyceride. And then some OH attached to the backbone, it became glycerol. And in the PFD on this right-hand side, that will be the triglyceride, and then the sodium methoxide, so that's from the glycerol and sodium hydroxide reaction. To produce the biodiesel, we're gonna need a mixing tank, and then heat a little bit with a heat exchanger here. Then there you have a separation tank where the biodiesel is actually at the top of the layer and the glycerol is at the bottom. Please note that some of the biodiesel is actually still on top of this glycerol. Actually not a pure glycerol. Referring to this reaction, we know that this glycerol has methanol, excess of methanol, excess of biodiesel, and then some glyceride, maybe diglyceride or monoglyceride. So there's lots of different things here. So we in this discussion, I'm gonna call this not glycerol, but crude glycerol. So that's actually the glycerol with various impurities from the biodiesel production. So why do we have to burn glycerol? Glycerol is a very nice chemical. You can convert it into many things. But the Indonesia biodiesel production from the Indonesia Biodiesel Association this year, they said we produce 10 to 12 million kiloliter per year, which means the glycerin is actually around roughly 10% of biodiesel production. So if we produce 10 million liter, then we're gonna end up like 1 million. So what are we gonna do with that? Lots of amounts of sorry. And then, okay, glycerol utilization. So there are a lot of things that we can do with glycerol as a pure chemical. So this was the map of chemicals that you can actually produce from glycerol. So lots of things, I'm not going to touch into the details. And for the industry, glycerol actually very useful. You can useful in food industry, drugs, personal hygiene, even the hand sanitizer, for example. We are needing a lot of hand sanitizer today during the pandemic, and some of the ingredients of the hand sanitizer, for example, is glycerol as well. But this is for pure glycerol. And first remember, previously I said that the glycerol that produced from the biodiesel production is not pure. It's crude glycerol. So it's still gonna need purification of glycerol. And first, purification is quite difficult due to the amount of impurities, and then the glycerol price is not really high. So even we purify glycerol from biodiesel production, it may not economic due to the economics maybe not fit for other pure glycerol like this. So that's from that point, we actually have the idea, what if we just burn crude glycerol? In the production of biodiesel, actually we need heat for the biodiesel production. So if we burn the waste from biodiesel industry, then the biodiesel industry actually can produce heat and power for loop system there. So which is quite interesting idea. But the problem is still have lots of impurities in the pure glycerol. Here I'll list some of the impurities or the impurities: water, methanol, biodiesel, soap. Soap is actually made from sodium, so it has lots of things, and then there's percent of water there, then we create soap. And that leads to the this research. So how is the effect of the impurity? Basically, what we do is solving the waste, the biodiesel waste, and these impurities, the concentration is pretty much showing in this slide. So the free glycerol, basically it ranges from 22 to 63%. It depends on the process and how good the process of transesterification. And we have methanol, water, few amounts of biodiesel itself, and then soap, glycerol, FFA, and everything else. So there are lots of impurities needs to be handled. So in this research is basically testing the idea of glycerol combustion, the crude glycerol combustion, and study if we burn glycerol, what happens with impurities? Is it help the combustion, or it's just make the combustion not possible, or even worse? So there are two ways actually. We study this research. First, we use the single droplet combustion to study the combustion characteristics. And then we use modeling as well, using mixing between glycerol methanol kinetic models. But for this talk, I will be addressing the combustion characteristics only, because for the kinetic modeling, we haven't published the paper, so I probably won't skip that one for this talk. But if you are interested, we can always discuss it later. So for the single droplet combustion, a few parameters that involve. First, the ignition delay, the ignition and combustion mechanism. And then burnout time, droplet size, and etc. So we have lots of combustion characteristics. And the experimental, for the combustion, single droplet combustion, the material we use is pure glycerol, water, methanol, biodiesel, and we mix the fuel in the impurities in glycerol with 5 to 15%, for example. It depends on what sort of range of the impurities in crude glycerol. So we work in that range. And then we analyze the droplet size using MATLAB, and then the burning rate, and the ignition delay time, the burnout time. For you who are not familiar with combustion research, the burning rate is basically the change of droplet size over time. So how fast is the combustion going? So that's the burning rate. And then the ignition delay is the time required for the droplet to ignite. So that's the ignition delay. And then the burnout time is the time to the whole thing to burn. And this is the combustion setup that I use. So we use a single droplet combustion using horizontal furnace. We have backlights there. We have a camera, and air temperature around 750 degrees C, or over just a little bit over 1000 K. That's simulate the temperature of a diesel engine. And the droplet size it was 1 millimeter, plus minus 0.1. And we use carbon fiber, or this one, this small attachment there, with a size of 0.1 millimeter. We try to find the smallest fiber that attach the droplet, but without, we can handle the high temperature. So the choice was on the carbon fiber. And we capture everything, the process inside the furnace with a CCD camera with 60 frames per second. And the basic principle is like this. So if you look at this image, the droplet, when the droplet arrives at the center of the furnace, pretty much like this, and then it starts to ignite, and then that's what we call the ignition time. And then the droplet will burn until there's no more droplet, just the fiber. So that's the end of the combustion, of the completion of the combustion. Okay, so we analyze the data. The droplet is very small. It's like only 1 millimeter. So we have image like this one. That's what we collect from the CCD, the fiber and the flame surrounding the droplet. And from that point, this is the basic theory of what happened with the droplet actually. So you have the droplet here, you have the flame front here, and then you have the temperature increase, and then the droplet radius is there, the flame radius is there. So the help of MATLAB, actually we wrote a MATLAB code to identify the droplet combustion. And here what we typically data that we can collect. So you have the fiber here, the filament, and then we have the droplet radius. This graph is actually plotting the grayscale intensity. So grayscale intensity is from dark to white. So if it's very dark, then it will be 0, and then white will be 100. So that's actually the sampling line over there. And then you have the droplet here, the droplet, and then you have the flame over there. So it's a bit high because it's a bit brighter here on the flame front, and then you have more darker area at the outside of the droplet. So that's how we measure the droplet size. And then because we know the diameter of the flame, the filament, so we actually can size of the droplet and the flame, the size of the flame. So we will know exactly how many pixels there, how many pixels here. So if we say this is 10 pixels for the filament, which correlated to 0.1 millimeter, then we know the size of the droplet and the size of the flame. And the next question is actually, can we burn glycerol? And we actually published one of our previous or initial paper studied the combustion of glycerol, and we compared with fuel, with the common fuel like diesel, biodiesel, and ethanol. And this is the typical crude glycerol droplet combustion. So you have the flame there, you have the droplet inside, and this is for the pure glycerol, and this is biodiesel, and this one is diesel, and the last one is ethanol. So the objective is actually to get a spherical flame, but that would be impossible on Earth because we have buoyancy. So the flame is pretty much like oval shape like this. I'm sure Yang can tell you more about burning droplet in the space, because I know Tsinghua sent 6 or 10 droplets into the outer space and burn it there. So I think that's the different level of research between the top 15 universities with us, for example. Okay, I'm going to continue for this talk. Delay time. The ignition delay time for crude glycerol and pure glycerol is actually quite high, which means it's not easy to burn compared to the other fuels studied. So that's consistent at any various temperature. And then if we look at the burning rate, the pure glycerol is actually quite low, so it's temperature. And then if we look at the burning rate, the pure glycerol is actually quite low, so it's hard to burn. It burns slowly compared to the other fuels. So here we have the experimental data and the calculation. So from this point, we know that some of the experimental data is actually a bit overestimated from the calculations, which is quite normal. And if we look at here, the burning rate is quite high. So we know the difference between pure glycerol and crude glycerol. Excuse me. We know the difference between pure glycerol and crude glycerol is only the impurities, which means there must be the impurities playing some roles in the rate of crude glycerol, and that would be interesting. So our research is basically finding which sort of impurities are playing that role. So what happened with the other impurities? So in the next, and showing us why glycerol or crude glycerol, pure glycerol, for example, perform. It has a high density, low heating value, low certain number, viscous, and it has a high outer emission. So probably that's the case. And okay, moving on to the combustion of. So from that point, we studied the impurities and select pure glycerol combining with a few impurities like water, methanol, and biodiesel. So PG is just pure glycerol, and this is water in glycerol, or methanol in glycerol, and biodiesel in glycerol. So in the setup, actually we have backlights for this purpose. If we turn on the backlights, we actually study the shape of the droplet. So if you're familiar with photography, if you have a light in front of you and then you have object and the camera at the opposite side, then you have the silhouette of the droplet. So what we capture here is actually the silhouette of the droplet, which can tell us the size of the droplet, the evolution of the droplet, whether there's a micro explosion or not. So basically, this is what we did. So we analyzed this. So with pure glycerol, there's not much explosion because we don't expect any explosion. It's a uniform fuel. But for water in glycerol, it produces, you can see here, it produces lots of micro explosion. From methanol, it produces like a large explosion. That's probably due to the methanol is very light, so it expands quickly in the droplet, inside the droplet. That's why it expands and create the expansion of the droplet itself, and then subsequently create the explosion. And for the one without the without the backlight, we actually study the flame. So you can see the flame of pure glycerol is quite dim. It's a very quite clean combustion, but if you compare with biodiesel, it has a bright yellow reddish color, which shows us that lots of soot involved in the combustion. So this is the typical image sequence that we can collect. So from the initial droplet entering the furnace, and then we have the first ignition there, and then the ignition the combustion completed, and then that's until the end of the combustion. So this image are the images that we are analyzed using the MATLAB. This one is for biodiesel because it's quite fast combustion, but for glycerol combustion, we have probably 1,000 images every time. So a lot of work we did was actually analyzing the image. And then about the droplet size, well, all the experiments actually comply with the square law. The square law is actually telling us that the droplet size is decreased with time during the combustion. So from the graph, pure glycerol with water, with biodiesel, with methanol, they all decrease with time. And then we can see a little bit expansion and here and here and here. That's because of the bubble formation and micro explosion. So there's no there's no way a droplet growing in size without the bubble formation. So this is telling us that yes, the droplet expansion is due to the bubble formation and micro explosion. And next we have the burning rate from the impurities. So the impurities with methanol actually increase the burning rate. If you look at this image here, so the increasing methanol concentration is actually increase the burning rate, as well as the concentration of water. The water concentration is a bit different. I'll come back to that point. So biodiesel as well, it increased the burning rate. But for water, the burning rate is increased at the beginning, and then at high concentration, basically it didn't change anything because there's no heating value of the water. There's no burning rate change. But if we increase the concentration of water, where this slight increase is due to the micro explosion and reaction of latent heat of evaporation, like that. And then what happened with the ignition delay time and burnout time? The ignition delay into combustion, then it gets slower for the combustion to actually happen. And but if we add methanol or biodiesel, the ignition delay will be reduced, and then the burnout time is reduced as well. So how about sodium or soap? So we know that sodium is bad for engine. And when we try to study the single droplet combustion with soap, it's very interesting because we actually can see that there's here that there's the like a solid residue formed and burned afterwards. So with the pure glycerol, you expect a clean combustion of a single droplet, and then with increasing pure glycerol with soap, with 5% of soap, for example. So you can see clearly that there's a solid residue at the end of the combustion, and then the solid residue was again due to the high temperature burned until the end of the combustion. The interesting part is the ignition time, burnout time, and total combustion time is actually decreased with addition of soap, but the burning rate is increased as you might expect as well. The sodium is burned. And the question is, where are the sodium? Are they in the flame or in the ash? Why this one is important? Because if it burn in the flame, then it should be ash, then it will clog the engine that you are using. That's why we need to find a lot of information more about that. So what we did actually, we checked the sodium presence in the flame. So we use a spectrometer. We combine the single droplet combustion rig with the spectrometer, and then try to capture is there any sodium, or if you have potassium as a catalyst, then we try to capture both catalysts. So the result or the finding is actually yes, the sodium or the potassium is actually burned in the flame, but not all of the sodium or potassium released in the flame. Some of the sodium or big part of the sodium or potassium is actually still in the ash. That's when we went to SEM image probability S. With increasing, we excessively increased the soap concentration. So with increasing soap concentration, actually you can see the difference. There's no porous structure. It just agglomerate into one big structure, and that will happen inside the engine when the ash agglomerate, and it will block, and it will clog the problem for crude glycerol combustion later on. So in the summary, we have a few interesting results. The impurities in crude glycerol is not everything. It's not all bad. Water, methanol, biodiesel still have, it still can enhance the combustion of the glycerol, which is good news. But the presence of water is actually, if you have more water, then the droplet can't be burned. So that's the bad news. The neat fuel like methanol, biodiesel actually can enhance the combustion due to their properties and then their combustion characteristic itself. But other impurities like sodium actually even if released in flame and ash, it can promote solid residue, which is not good for the engine. And from that point, we find a few new gaps. So water actually promotes optimization, but one thing that we learned from there, we didn't know how much is the maximum water content. Water is quite troublesome because first from the material from palm oil, for example, it contains water, and then there's water during the cleaning or the flushing. So to uh, clean out the biodiesel from the mixture, normally people using water to flush then this flush goes with the crude glycerol, which can increase the content there. So we need to identify how much of water, and then much more further research is required to overcome the effect of sodium or salt. We know that's gonna be bad news for the engine, and at this stage we haven't touched how we go around to solving this issue yet. So if there's any collaboration research, that would be very interesting. Had we finished with the soap itself, we haven't tried the crude glycerol combustion engine, so it's very open for the next batch of research. Or we can utilize the crude glycerol as a fuel with other methods, for example, for hydrogen production using Zhijian catalyst, and then the hydrogen we can burn in a Yang's engine, pretty much like that. Oops. And the last, I'd like to acknowledge a few people, the late Professor for the beauty of science, and then Professor Elisa Hambali, who really dragged me into biodiesel, renewable energy, and my academic father, our academic father, Yang, not Yang, Zhijian Mayang, Professor Zhang, and then our partners for this research project, IRC Linkage Project, and PhD Bilton and ANZAC, and Australian Commonwealth Government for Australia Award, and then my CFA, my lovely CFA colleagues, Zhijian, Yang, Mayang, and Miming, Zino, and other people who are involved in this research. I think that's enough for me. Chair.
Yeah. Thank you, Dr. Hendricks. Very interesting topic and research, and hopefully we can further advance the research gap that you have mentioned, and hopefully the research can also be done here in the future, inshallah. Okay, because we are running out of time now, I would like to invite Dr. Mayang. Before that, I will read the short CV of her. Okay. Okay, Nimas Mayang S. Sunyoto, PhD. She finished her bachelor degree from Agroindustrial Technology, Universitas Brawijaya, and studied finished doctoral degree from University of Western Australia. So actually for this virtual international seminar, we have a very good collaboration with University of Western Australia. And for Ms. Mayang, she works, currently he works as a lecturer at the Department of Agroindustrial Technology. And she has also viewed a position within our faculty, head of ULB, which is like English unit in our faculty. and head of clinic journal, as well as a member of Sbistec research group. Her research expertise is about bioenergy and bioindustry. Various research experience has been carried out in terms of like waste to bioenergy, wastewater treatment, and waste resource. Okay, Dr. Mayang, I would like to invite you to present your research work.
All right, thank you.
25 minutes.
Okay. Yeah. Thank you, Dr. Sri, for the kind introduction. So, first of all, I would like to thank the Department of Agroindustrial Technology and the head, Dr. Setyawan, and also our research group, Sbistec, for giving us opportunity to share some of our research interests and also research funding on today's webinar. It is a very nice day for us to be here together to share with all of the participants for possible discussions and also collaboration, as well as I would like to formally welcome my previous friends and colleagues from Center for Energy, University of Western Australia, Dr. Zhang, and then Dr. Zhijian, and also Dr. Hendricks Julius Setyawan, that has been with me, taken care of me until in the position where I am now. Okay, so following up the topic that has been delivered by the previous speakers, so mostly about the biogas to waste to energy using several different routes. So it is my turn to then present one route of the biofuel production via two-phase anaerobic digestion. So actually it is really closely related to Yang's study, because he also done a study, like a follow-up study from my study, which investigate about the possibility to mix the hydrogen into the biogas for spark engine application. And my part is how to produce that type of biogas via two-phase anaerobic digestion. And particularly in this presentation, it also referred to a certain bio-based material called as biochar. So probably, as we already know, that anaerobic digestion is already stable, like a major technology that has been used for decades, even for maybe centuries. But then in the past decades, this then regained attention because the role of the AD is not only a means to treat waste or wastewater, but also to produce energy, right? So it's also in line with the maybe sustainable development goals that we try to achieve within several years from now. And then it's actually also been applied in both in developed or in developing countries. For example, if you see in the figure, it is an example of a wastewater treatment plant that treat wastewater as well as to produce biogas. In Perth, this is the wastewater that I got my inoculum for my study during my PhD in the University of Western Australia. And also in Indonesia, I think like Dr. Sri Buneneng already explained to us that in Indonesia, we also have many types of feedstock and also industrial wastewater that can be used for the feedstock. For example, wastewater from palm oil industry. So we can use that. So briefly, this figure 2 shows us the global biogas plant. So if we compare to the energy generation in China, like what Yang's already described, the energy derived from biomass is pretty low. But then if we see the global trends here, it may make us a little bit feel relief that from, for example, the past 2 decades from 2000 to 2000 has improved like around 8 times. So it means that AD itself is a potential means to produce bioenergy. And if we take a look a little on the fundamental of the anaerobic digestion in the figure 3, we can see that anaerobic digestion here is a process that involves several biochemical reactions that is concentrations of oxygens. So that's why it is called as anaerobic digestion, right? And the steps here, usually conventional anaerobic digestion is conducted in a single phase anaerobic digestion where the 4 steps of the anaerobic digestion, hydrolytic bacteria, which of course kind of ideal optimum condition for them to grow and also to do the activity and then the reaction. And then acidogenesis is the next step where the acid from the acidogenesis is converted into acetic acid. And then the last part is for methanogenesis, where in the acidogenesis, where it produces hydrogen, so it produces 2 types of product, which is hydrogen and some small trace gases, and then the other is acetic acid. In a single phase anaerobic, all of the hydrogen here is converted into CH4 or methane by hydrogenotropic type of methanogens. And then the other one, the other groups of bacteria called acetoblastic bacteria convert the acetic acid into the methane. So everything happened in a single phase. So it is stable technology, but sometimes if the load of the feedstock quite high, then it will be cumbersome. The reactor sometimes can be failed. But then in the stable operation of biogas plant, it usually can run very well. So it really depends on many factors. So at the end of the operation, consists of methane around 50 to 75%, and CO2 around 20 to 45%, and then some of the trace gases. Okay, so there are no hydrogen in there because all of the hydrogen has been converted into methane. And as we already discussed, that AD, single phase AD, has been widely applied in many types to treat many types of waste, like food waste, industrial waste, poultry, and then dairy, maybe sugar factory, we can name it. And then from domestic, and also to treat the sewage sludge in wastewater treatment plant, it also is used. But then if we come back to the sum of possible problem in the single phase anaerobic digestion, we learn that it is operated in suboptimal condition. I mean, it's okay, but maybe there is a room for improvement, like to give each group of bacteria their optimum conditions so they can work well. And then secondly, it produces low quality of biogas because it contains high carbon dioxide. So it has a poor ignition quality and slow burning rate. So with this problem, we need an alternative to overcome these drawbacks. some of the researchers are now interested in the system called TPAD, or two-phase anaerobic digestion. So that having known about the fundamental of the anaerobic digestion, then we move to the comparison between single-phase and two-phase anaerobic digestion. So if we still remember about this picture, right? As I told you, in the single-phase anaerobic digestion, all of the reaction happen in one vessel, and it may be cumbersome or have a problem if it has a high loading rate. Yeah, so then in the acidogenesis, hydrolysis and acidogenesis part, it can make the medium become so acid very easily. So the pH will be dropped very sharp, and then it can cause the reactor failure. That's why the idea of the TPAD is to separate these two big reaction into two different vessel or reactor. First is the first phase anaerobic digestion, which at the end of the process will produce hydrogen, and then the second one which produce methane. So at the end of the process, these two streams of gases will be mixed. Already told us in the first presentation that the addition of hydrogen in the natural gas, or maybe the biogas derived or generated from AD or TPAD, yeah, it will improve the quality of biogas if it's used as biofuel in engine. Okay, so that's probably the idea of why the TPAD now attract the attention of researcher, and it brings us to the background to study about this two-phase anaerobic digestion. So at the Center for Energy of UWA, we try to design or develop this concept into a big system. We call it TPAD system. So basically, the main component is the first phase and the second phase reactor of TPAD, and then it will involve the preparation of the feedstock, and then it will goes to the first phase until it reach a certain total solid that is doable for the first phase to do the hydrolysis and acidogenesis, and this first reactor is operated in a lower pH because hydrogenotrophic bacteria like to work in a lower pH, like around 5 to 6. And then they like also higher temperature compared to the methane phase, as well as shorter retention time. That's why when it is designed, the first phase volume is much smaller than the second phase, because the time for the first phase to treat the reactor is very fast compared to the second reactor, which is very slow. So from the first phase, it will produce hydrogen, biogas, hydrogen-rich biogas, and then the effluent, which is acidic because the pH is around 5 or 6. Then it will be adjusted into around 7, the natural one, and then it will be pumped into the second phase. In there, we put a methanogenic archaea, and it will convert the acetic acid from the first phase into the methane. And then after the gas stream is there, the mixture of the hydrogen and also methane, it can be further cleaned and then used in a gas engine for combined heat and power generation. That's probably Yang already mentioned to us before. And then lastly, the effluent from the second phase can be further conditioned to make organic fertilizer. Okay, that's one part of the concept that it is already built in our center. So the unit is designed for a portable biogas, hydrogen enriched biogas production especially for the remote communities, for maybe to be used in a farm or in the rural area that have a limited access to electricity. Yeah, so it comprised of the first phase reactors around 150 liter, and then at the other side is methane production bacteria, second phase around 500 liters. Okay, so that's one part of the story, which is the TPAD vs single phase anaerobic digestion. And then on the other hand, we also have this potential called biochar, which probably already explained by Zhijian before. So from the pyrolysis process, the pyrolysis process can use many types of feedstock. Maybe in Indonesia can use empty pump, fruit bunch, or TKSS, or maybe other potential solid waste, agricultural residue, maybe food waste. It then can be pyrolyzed in a pyrolysis reactor, and then in a certain temperature, like around 300 to 800 degrees Celsius, with no oxygen, it will then produce three products: oil, char, and then gas. This thing, char, biochar, will be used as the specific material that we try to make to enhance our hydrogen-enriched biogas in TPAD. Although actually it also has many kind of application or role. For example, for the absorption, also agriculture and carbon sequestration. Okay, so that biochar we used in our study derived from pine wood chip, and it is heated in an indirectly kiln reactor, 650 degrees Celsius for 30 minutes. And we can see that by microbes. And several studies has been done on the biochar utilization in AD. Yeah, it is really increased significantly from where I studied my PhD back in 2014. So it was just still rare at that time, but now it's quite increased quite significantly. But then when we see the study, most of them study on a single phase anaerobic digestion. Either it's to produce hydrogen or to produce methane solely. But then because of our aim to improve the quality of TPAD, we must use TPAD. That's why we would like to see, we would like to analyze the effect of biochar on two-phase anaerobic digestion. So this is like, it's one thing. This question is like our biggest question is like, so does biochar enhance the TPAD performance or the production? So what we do is to test the biochar, to add the biochar in each phases of the TPAD, and then we do that first in a small scale, bench scale, and then later on we kind of jump into process demonstration unit that I have already discussed before. So for the case study in our center, we use the pinewood biochar on the bench scale study. It used very small vials, around 100 milliliter, just to see does the biochar affect the biogas production. So we use simulated food waste. We use a white bread at that time, and then the inoculum for the Woodman wastewater treatment plant. And we add a series of different ratios of biochar from 0 to 33.3 gram per liter. And then we monitor the gas volume and composition daily. And if we see in the result in the first phase of anaerobic digestion, we can see that for the lag phase, so we actually monitor the hydrogen and the hydrogen production daily, and then we plot the cumulative value of it, and we fit it against modified comparison model that it is usually used to analyze the trend of the batch system of biogas production. And we can see that clearly the lag phase of the system without biochar produce the hydrogen quite slowly, while the others do that, I think, less than 12 hours. And then it increased until at the end of the operation around day 7. Accomplishes around 140 milliliter per liter of the volume. And the highest cumulative is achieved by the treatment with 8.3 gram per liter. And it's significantly different if we compare it to the control. So what we can see is the biochar addition at some point can increase the production of hydrogen, but then if we put too much, it will then hurt. It will upset the system. So that's why we need to work on that to see which the optimum addition of the biochar. Yeah, if we can see the possible mechanism of how biochar can enhance the hydrogen production, is probably because of the ideal properties of biochar itself. Because as I told you, it contains nutrients and also micronutrients. So it provides nutrients, the micronutrients there also helps the system to produce kind of important enzyme for them to grow, and then also to enhance the microbial growth and activity. And also with the surface area, it produces large surface to initiate the biopium formation, so that the bacterial community is more robust. That's why it can produce the hydrogen sulfide faster, also to generate VFA faster if we compare it to the one without biochar, and also the structural lag phase. And during the production, the biochar itself tries to help to buffer the medium, so it provides a sort of a favorable condition compared to the control. Because at the end of the study, we checked the pH, the one without biochar reached around pH 3, while the one with around 16%, more than 16%, it can still buffer around 3.5 or 3.6. So that's why at the end it produces higher cumulative hydrogen production. And then for the second phase of anaerobic digestion, it is also interesting because we can see very clearly the lag phase differences with and without biochar. I think the lag phase here was reduced by 50% compared to the one without biochar. And then later on, after the cumulative production at the end of the study, so the hydrogen production lasts for 40 days. So we need to wait until the production is really stopped. And then we can see this trend that the one without biochar produce biochar biogas slowly, but not at the end. It outnumber the treatment 25 and 30.3. It means that we need to make sure at a certain point the biochar and the content of the micronutrients, they're not always happen to support the hydrogen and methane production, but sometimes also can inhibit the production itself. Okay, and for the CH4 production, it differed from the first phase, because when we check the pH at the end of the production, the pH difference between the one without biochar and with biochar are similar. Is not significantly different. Yeah. But then we suspect that still the remaining micronutrient may really support the microbial growth. So the lag phase can be significantly shortened. So one of the students in our center, Mr. Yusron Sugiarto, which is like a staff in our faculty, the Department of I think bioprocess. Yeah, he is now continuing my study on this to see the leach micronutrient, which type of micronutrients that really affect it directly. So he also do some research on the effect of the micronutrients to the abundance of the microbes in there. Yeah, and from the SEM, we can also see the biochar provides a good surface area for the microbes to build the biofilm. So probably we couldn't see the one inside the biofilm that it make the microbial growth more robustly. Yeah, so that kind of mechanism. So the surface area and also the remaining leach nutrient is suspected to be the cause why the methane production is higher. Okay, and then moving on, after we do the bench scale study, move to the demonstration study. So we do the startup. We just do the startup separately between the first and the second phase, and we add the biochar addition in there in the volume 150 in the first phase, and then the second phase is 500 liters. And the startup strategy we adapted is a feed batch to allow the microbes to adapt, and then followed by the semi-continuous operation. So we don't feed the reactor to 24 hours fully, but we just fed them like once a day in a certain time. So in this startup, we want the microbes to be enriched and to adapt to the system. And then in this semi-continuous operation, we learned that the peak hydrogen composition reached around 49%, which is not bad. And also the yield is around 46 liter kilogram per VS, which we can say it's lower than the common study that has been done. It's probably because of the strategy that we use, and then at that time we haven't really connect the first phase into the second phase. So the volatile fatty acid accumulation was there, and it then reduced the yield of the hydrogen. But for the methane production, we can say that, yeah, it's still comparable. Yeah, if we try to compare with other study conducted by another researcher. Yeah, so let me just wrap up the conclusion of this sharing or presentation, that we can see that biochar in the context of two-phase anaerobic digestion, we can see that it can shorten the lag phase and then increase the maximum rate and also cumulative of hydrogen and CH4. And then for the first phase, the biochar role mainly to provide nutrients to kickstart the reaction. So it has a shorter lag phase and then high surface area for the microbes to attach, and also to buffer the medium during the production. And then for the TPAD in the second phase, biofilm formation, and also the remaining nutrient was suspect to be the cause of the increase of the methane. And then the strategies, although it's not been good yet, so we hope we see that it's promising, and we just need to evaluate another strategy to enable the operation of the TPAD in a process demonstration unit. And then for the further studies, we really need to see the underlying mechanism in a very detail. For example, in a microbial identification of each brew, and then try to use like different types of biochar and see what is the what characteristic beneficial to the production. And then we also need to study the long-term continuous TPAD. And last but not least is also the techno-economical study on this, especially when we would like to integrate the pyrolysis plant, which has been discussed before, and then the TPAD so it will be a whole system of like biomass. So I also would like to acknowledge is also the supervisor where me, Yang, and also Hendrix and Zhijian is belong to his family, and also Department of Agroindustrial Technology, UB, and also Sbistec for giving us the opportunity. We also hope that we can go in Indonesia about the development of biogas in Indonesia for providing the project fund and also Australian award scholarship for me. Yeah, this is the reference that probably interesting to see about the biochar and TPAD production. Yeah, I think that's all for my presentation today. I give back to Bu Neneng. I think
thank you, Mayang. Okay, so we are now moving to the question and discussion. Actually, Mr. Mayang, very interesting. Hopefully, we can further working together, inshallah. So we have a very limited time, but we have a few questions from the audience. I will read first the question for the first speaker, Dr. Yang. So we have three questions for you, Dr. Yang. So the first question is from Mr. Muhammad about how to purify hydrogen. For example, like hydrogen sulfur.
Just receive an invitation to open my camera. Am I okay? Yes, I think I'm okay. Yeah. Actually, so basically we have two steps. The first step is if the gaseous fuel is from a pyrolysis or a gasification, basically we will have hydrogen, carbon monoxide, CO2, and water, etc. So CO2 and water are relatively simple for us. We can use, the different vapor pressure to separate CO2 and water from hydrogen and CO. Well, CO is more, CO is more complicated. First, we need to use water gas shift to enrich the hydrogen production. The second, the most commercialized technology is use the PSA, pressure swing absorption technology. We need some film. This kind of film can separate, can basically absorb hydrogen. Hydrogen can go through this film, basically, and CO, and this film will keep CO at the other side. So at the target gas, we will have a very high concentration of hydrogen utilization, hydrogen concentration. However, relatively, this technology is expensive. So basically, this technology is used for fuel cell. Fuel cell, especially the hydrogen fuel cell, hydrogen proton fuel cell, it need a very pure hydrogen concentration. For our application, we need to maintain the CO at an acceptable level. That's it. And not because CO is bad as a fuel. It is because CO is toxic. If the gaseous fuel still contains some of the methane, it doesn't matter. Anyway, we will blend these gases into gas pipes. So that's it. So basically, that's the strategy. It depends on the cost that you want to pay and the final target. If the final target is just heat, we just want heat, and the heat demand is localized. For example, we have a unit generating hydrogen just not far from my home. Yeah, we can directly use gas pipeline. It contains some CO in the gas pipeline. It doesn't matter. So probably 20, 40 years ago, in lots of cities, we still use townhouse coal gas, town gas, coal gas for our heat supply. Now, for long distance gas transportation, CO should be considered. We need to remove CO. Okay, so and for fuel cell application, we need to remove CO and get a very high purity hydrogen as our feedstock. So that's the answer for this question. Am I clear?
I think it's clear. So maybe we can move to the second question.
Okay.
So the second question is from Professor Udin Hasanuddin from University of Lampung. The question is, I think you know that during anaerobic digestion, we can arrange digestion condition to produce more hydrogen. So the main composition of biogas become methane, carbon dioxide, hydrogen, and other gas. Did you have any experience to evaluate effect of hydrogen concentration on biogas?
It's a very good question. Basically, I think I published one paper talking about this question. Of course, hydrogen, a high content of hydrogen, high concentration of hydrogen will affect the combustion characteristics of the overall gas. My opinion is that if we are talking about two-phase anaerobic digestion, okay, because CO2 is also contained in this gas, right? CO2 is is a weak point of this gaseous fuel. It will weaken the ignition. It will make the overall combustion process more easily to be extinguished. Okay, in that case, we can introduce some hydrogen into the system. It will pull the whole system back to the trail. Okay, so basically, if we have hydrogen and also we have CO2, we can have kind of overall combustion characteristics, which is natural gas. That's I think that's the way. Is there anything bad happen if we burn biogas with high concentration of hydrogen? I think that depends on the situation. If the concentration, if the composition of the gaseous fuel is constant or change not so significantly, for example, we can maintain a hydrogen concentration above 80%, but below 90%. We can design, we can optimize the system and let the a combustion device to be at its best condition when burning this kind of biomass. The problem is from the variation of this gas concentration. For example, if you want to blind some hydrogen into the biogas, if the hydrogen concentration changes from 0 to 80%, that will be the problem. That means we have to make a very smart engine or very smart combustion device which can sustain a very good combustion performance when the variation happens. I guess that's the problem. So during my talk, I'm talking why we need to define a blending limit, upper limit for hydrogen. Actually, if we can define a new engine, there is no limit. But the situation is we have engines in our home, we have ovens, we have stoves in our home. It's already there. We cannot make a very great modification to that system. Okay, so that's the true problem here. So I guess no problem to burn high concentration of hydrogen in our biogas, but if the concentration keep on varying, that will be the problem. Okay. Oh, sorry. Moderator, I think you close your mic.
Yeah. Thank you for Dr. Zhang for your answer. So I hope Professor Udin are satisfied. If not, we can communicate further. Move to your final question from Tutut from Universitas Brawijaya. Which source of biomass that you think will be the best source for biochar for fuel cell in terms of the catalytic capacity?
I'm sorry, I'm not an expert for fuel cell or the catalytic process. I think probably Zhijian has more experience regarding this question. But what I think is that the biochar is good for generally, general. It's for dealing with relatively low rank tar-like fuels. For example, if we have a pyrolysis process or gasification process, we will have some of the production, like oil. We call it tar, right? It's very acid and sometimes not so stable. We can use biochar as all these long chains of molecules to small pieces to increase the hydrogen methane production. To increase the light molecule yields. Well, for fuel cells, I guess if we are talking fuel cells, the need to be very clean, right? So I guess biochar won't be a very good option for this application. I guess I'm not an expert for this part, but my guess is not none of these biochars is good one. Well, if we are talking about a very rough or thermal process such as pyrolysis and gasification, I think the best biomass is the cheapest one. Which one? It's very economical. You choose that. Okay, so that's my answer. Thank you.
Okay, thank you, Dr. Zhang. Now I want to read two questions for Dr. Zhijian. Sorry, we need to move very quick because the time is running out.
I'm here.
Yeah. From Yuana, University of Bengkulu. Question to Mr. Wan. Is it possible to produce gasoline from biomass by using a simple method appropriate was applied to small producer? Thank you.
Actually, we can have some liquid from biomass pyrolysis, but Depending on the conditions, the liquid can, normally is not in the range of gasoline hydrocarbons. If we want to have a relatively high quality of gasoline, we still need to go through this methanol conversion process. If that means we need to get methanol first. So in doing so, we still need to convert biomass into syngas because syngas is used for methanol synthesis. Then we convert the methanol into gasoline. That's my quick answer for this question.
Okay, thank you, Dr. Wan. So the second question is again from Professor Udin Hasanuddin from University of Lampung. I think the production of gasoline through MSR is very expensive currently. What do you think if we produce gasoline from palm oil? Is it possible to use a kind of your catalyst? Thank you.
I think Professor Udin is right. The energy process is very expensive. Currently cannot compete with the gasoline we get from crude oil. And it's reported. It has been reported only the price of the crude oil is about 140 US dollars. So for use palm oil as a source for gasoline production. Again, we go back to the same answer. Again, we still need to, if we want to get gasoline from methanol, we need to have methanol first. Then we still need to convert palm oil into syngas, and then convert syngas into methanol. I guess perhaps it's still not that profitable to currently, based on current technology and the price of crude oil. Even use palm oil is still not profitable. It's because currently the gasoline is still cheap enough. That's my answer. Quick answer.
Okay, thank you. I think you also typed the question, right, in the Zoom chat.
Yeah, that's right. Yeah, that's right.
Okay, then thank you, Dr. Zhijian. Now, I want to move to Dr. Mayang. We have 3 questions for you. First is from Yuana, University of Bengkulu. Is the produced biogas from the first phase ready to use safely for daily activities, like cook, for example?
Okay, so actually, as we already learned from Yang presentation, so probably for the hydrogen production, because first it still contain like high concentration of CO2. Yeah, it probably is not optimum to use, and then to use because the hydrogen, it's probably become dangerous, as Yang already told us. So it needs a certain limit or a certain safe way to utilize the hydrogen for the daily usage. So the safe way is just to mix it with the CH4 or methane, so it can compensate the reactivity of the hydrogen, especially if it's to be used in the daily usage.
Yeah. Okay.
Yep.
Okay, Mayang. So I move to the second question. This is from Mbak Sasha, Universitas Brawijaya. So since you use the natural inoculum for certain sludge, then have you ever compared the efficiency of your TPAD by using pure culture or another source of inoculum? If yes, how was it? Is there any information about what is the majority microbes in inoculum you use?
Okay, thank you for Busasa from Yamaguchi. So actually, in our study, we use mixed cultures obtained from the Woodman Point wastewater treatment plant, right? And it is a mixed culture, so we just use it as it is, especially for the methane production part. But then for the hydrogen production part, we heat it up into 95 degrees Celsius just to select the hydrogen producing bacteria. So we need to remove the methanogens from the first phase. In my part of study, I haven't done any microbial study on this, but then Pak Yusron follow up with this question of research. Yeah, I think from our discussion lately, so yeah, it is found that the abundance of the bacteria in the first phase is mostly, I think, Clostridium and Firmicutes. So in not specifically in one species type. Yeah, we haven't gone too far to there. And then for the methane, I haven't really sure about that. Just wait for our collaboration of the publication. Hopefully, we will publish it this year or next year. But the important is in the class of acetoclastic archaea, because in the second phase, the most methane conversion is from acetic, not from the hydrogen. So we might be sure about the group of that is acetoclastic archaea instead of the hydrogenotropic. Yeah, so we would like to collaborate if Busasa have any resource or facility for us to collaborate.
Yeah, okay. Thank you, Dr. Mayang. So we move to the final question for Dr. Mayang. It is from Khairun, Universitas Jember.
Yes.
In the semi-continuous system, how to manage the optimum condition of the first and the second reactor, such as the pH? How much is the efficiency of using two-stage fermentation system compared to the AD system? Can you share your?
Okay, thank you, Dr. Hayden, for the question. So for the first question, for the continuous system to manage the optimum condition, because if we talk about the semi-continuous, so it means when we work in the project demonstration unit, right? So the facility is equipped with like an automatic pH meter and also the probe for the temperature. So then it can give the information to us like the real time pH in the reactor. But then we also, from time to time, we also need to check the sample from the culture to check the pH manually, so that if it is under the wanted or the optimum condition, if it's too acidic, then we need to add sodium hydroxide. While if it's more than the neutral, we need to add hydrochloric acid, but mostly we need to add sodium hydroxide because mostly in the first phase, the pH will go drop very, very fast. Yeah, and then one of the attempt is by using the biochar so that it will not, too demanding for us to put the sodium hydroxide. But for the second phase, it's quite stable for the pH. Yeah, it's quite stable around 7. So we don't need to worry about the second phase. The first phase is the cumbersome one. And then the other about the efficiency. If we talk about the efficiency, maybe we can look at 2 different points. First, probably in the aspect of the organ, like the organic or the total solid reduction, right? Because it is a means of wastewater treatment. Yeah, so In our study, we didn't look further on that because we really need to know about the hydrogen enriched biogas generation instead of the performance on wastewater. But then based on the literature, probably about the reduction is quite the same with the single phase anaerobic digestion. It's around 80. Yeah, it depends. Really depends on the feedstock, the operation condition, the reactor and stuff. So that's why we need to check each time. But then the range is around 50 to I think 85 to 90%. So it's quite similar to single phase one. But then in the aspect of bioenergy, we get a benefit from the improve the biogas quality. And then for the reference of my paper, I already put some of my literature in the reference in my PowerPoint today. Probably the seminar committee will distribute the PPT later. Thank you.
Yeah, thank you, Dr. Mayang. Now there is a question for Dr. Hendrix, yeah, from Agung, University of Malaya. In your opinion, how big the potential of developing glycerol as raw material for fuel production, particularly in a big-scale industry? What things have to be considered for it? Dr. Hendrix.
Okay, thank you, Chair. Thank you, Pak Agung, for the question. So, as inside, for fuel inside the biodiesel production or biodiesel industry, I think it's still possible. But if we use it as a fuel in a diesel engine, that would be problematic due to the sodium content. But if the crude glycerol is burned using like a simple burn, it's still problematic, but it can be another way to overcome the solid residue that the solid particles, not solid particles, the solid ash that created from the combustion of glycerol. But for developing glycerol as a raw material for fuel, for a commercial fuel, I think we still have a long way to go there. Because first, glycerol heating value is quite low. It's only 18 megajoule per kilogram, comparing to gasoline, for example, or diesel, like 45 megajoule per kilogram. So regarding that, I think a few years ago, we published a paper by mixing glycerol with some other fuel to overcome the issue. First, to make it not too viscous, we add methanol in the mixture, and then to increase the heating value, we add charcoal. So we can have like a higher heating value, but it's still under development at the moment. So I think it would be a very interesting future research to develop glycerol as a fuel, because we have in Indonesia or Malaysia, for example, we have lots of biodiesel production happening here. I think that would be my answer, Jack. Thank you.
Yeah. Okay, Dr. Hendrix. I think we are now on the final session of today's event. All the question has been answered by the keynote, the guest speaker. If you want to discuss further later on, the committee, the webinar, the virtual international seminar committee will provide you the PPT slide of all the guest speaker today. And I think there is a contact detail, right? The email of the email address. So if you are interested to discuss more further, you can contact them privately. Okay, before I hand over to the host, I would like to say hello to Dean of Faculty of Agricultural Technology, Professor Imam. Professor Imam, he's supposed to open this session this morning, but because we have accreditation online for our master degree in agriculture engineering, so hopefully our dean will be able to close our session today. So okay, before then, please allow me. I'm a novice. Yeah, please allow me. Usually in our seminar, we always recite the pantun. So please allow me to share with you my first pantun ever made in my life. Okay. So here is the pantun. I take bus on the subway and saw the moon from afar. Fossil fuel, please move away. Biomass to bioenergy, be the star. Thank you. See you again in our second virtual international. Please stay tuned. Okay, Mr. Kamal, I hand over to you. Thank you very much.
Thank you very much.
Thank you, Bu Neneng. For the Miss Prof. Imam, would you to say a closing statement for this webinar?
Okay, thank you very much to Mr. Kamal. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone who already joined with virtual international seminar. The topic is biomass to the bioenergy, and I significant or serious appreciate to the Department of Agricultural Agroindustrial Technology, which already conduct this seminar, and also for the participant who already joined with the seminar. We hope we meet with the seminar because our faculty and our department create many webinar with many topic, I think, and we hope all of topic help us to improve the knowledge, maybe sharing the information and experiences in research and publication, and of course in implementation and the field, especially how to improve the small medium enterprises in agro-industry, and of course how optimize our natural resources. So thank you for everyone. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you for Prof. Imam Satoto as the Dean for the closing statement. And thank you also to the moderators who has guided this event very well today. We also thank to the speakers who have shared a lot of knowledge that is very useful for us, as well as the participants who have attended this event, and also the organizers committee who had prepared for this seminar today. At the end of the event, as the host, I would say thank you and apologize if there is a mistake during this event. See you all for the next webinar. Good afternoon. Wassalamualaikum warahmatullahi wabarakatuh. Please, for the presenters and committee, please remain on this room for we take a documentation.
Yeah, I think for all the participants, can you please turn on the video? So we
please, for the participant, turn on your video.
To take the picture.
Okay. For the first page, okay. For the second page, please open your video. Okay. For the third page, please open your video. Okay, thank you. It's all done for the participants.
Okay, thank you.
Thank you, Pak Udin, Prof. Udin.
Thank you, Bapak.
Thank you, Pak Imam.
Thank you all. Thank you, Yang. Thank you, Zhijian.
Thank you.
Assalamualaikum.